Hi guys, you can all hear me? I can hear me too. So as Alex said, I used to work with him and Mike Nash. My history is like 10 years of .NET, and I've been slowly crawling my way out of that pool into the Scala and Spark world. I'm here today to talk to you about Spark 2.0 and the main addition to the library called structured streams. Before we start, is anybody here has never put Spark into production? Okay, good. So this presentation is going to be, we're going to cover a lot of the context of Spark. So you'll get a really good overview of the Spark libraries, and then we're going to spend 10 seconds at the end on structured streams. So if you haven't seen Spark before, it's the back of the box is something like a big data general compute engine, a distributed general compute engine. The main library is called Spark Core, which is the bottom rectangle there. And then on top of this is 4 specific use cases: GraphX for graph computation, machine learning, a streaming library, and Spark SQL for structured data. And when we say structured data, it means your tabular data, SQL tables, CSVs, JSON files. The main thing to know about Spark and what makes it work is an RDD. It's a resilient distributed data set. And to build up your mental model of what an RDD is, just imagine a parallel collection. That's the very basic thing to think about, but there's a lot more to it. You can see the quote, it's a parallelized, lazily evaluated, directed acyclic graph of computation. So we understand the fact that it's a parallel collection. What it also is every time you transform your RDD collection, it's immutable, so it gives you a new one. And as you do your maps, flat maps, and filters, you get a sequence of RDDs. And these RDDs, you can imagine that they're actually nodes in a graph that remember the previous nodes. So this concept is called lineage. When one of your machines on your cluster fails, RDDs can rebuild themselves all the way back to source data using this lineage feature. The second thing to know about RDDs is that there's a difference between transformations and actions. So a transformation is anything that produces a new RDD. So again, your maps, your filters, it just gives you a new collection. And these transformations don't get executed right away when you call them. They only get executed when you call an action. So it's like a lazy evaluation / delayed evaluation. So here's an example of the RDD API contrasted with the Scala API. If it's Saturday afternoon, if you guys are feeling a little jittery because you haven't had a drink since Yelpworks party last night, we're going to play a little drinking game. Every time you see a word count example, you can have a shot. So word count is the hello world of big data. You count all the words in a corpus, and you output the number of times each word appears. Right, so in Scala, it's fairly simple. Here I have words, which is a very long string, lowercase, split, group by the words, and then get a sum of the values in the key value pair. So you see the Spark version is extremely similar. I have a map, I have a flat map, I have group by, and I have a map values. And SC, the Spark context here is your entry point into the Spark framework. So this counts as 2 shots. And here's Spark provides you with a web console to visualize all the work it's doing. So this is a snapshot of the web console, and it's our word count in graph form. So you can see here every operation I did added a node to my graph of computation. And if a computer fails, it uses this graph to rebuild itself. So that's RDDs in like 5 minutes. There's a lot more to it. But keep this in mind because this is the special sauce that makes all Spark work. And so keep this in the back of your mind as we talk about the following libraries. So the first library I want to introduce is the Spark streaming library. We're talking about structured streaming later on. So this is kind of, I don't want to call it old, but it's the current streaming library. And the way it works is that instead of RDDs, we have what's called a D stream, a discretized stream. And the D stream spits out RDDs every like interval that you give it. So the minimum is half a second. I don't know what the maximum is, but it wouldn't be a stream if you put it like 5 minutes. So let's say every half a second, you get a new RDD, and then you do some sort of transformation on the D stream, and you get the D stream back, and then you get another D stream, and then from that D stream, you have a bunch of RDDs that you operate on. So this is kind of what the computing model for Spark streaming looks like. You have these time intervals, so every half a second, your D stream is producing a new RDD. And you operate on it by, with windowing operations. So you imagine if you're Twitter and you're counting the trending tweets, right? You say, I want the top 10 hashtags in the last hour. The hour is your window, and if you're updating that every 10 minutes, that 10 minute is your slide. So in the dstream API, there's a little bit of extra cognitive load because you have to think about windows, slides, and you have to think about the fact that your batch interval has to be, your slide has to be a multiple of your batch interval. And while it's, maybe it sounds simple, but this has been a severe pain point for many people. So here's the streaming version of word count. And it's, you can see it looks very similar. I have SSC here, and that's the Spark streaming context. So you create a Spark context, and you get a Spark streaming context out of it. And I'm monitoring a directory, and each time a new file comes in, I'm going to get a discretized stream of sentences. So I do all these operations, and I get another D stream back. So while that's cool, my mind is about D streams and not really RDDs, right? And I have to think about my intervals and my batches. And dude, I just want to do some ETL. Why am I thinking about all these other things? The next library we talk about is the Spark SQL library. And this comes from, if you're a data scientist, Python Pandas is a popular data science library. So the Spark SQL library and the data frame abstraction are inspired by the Python Pandas. And again, this is a library to process and compute structured tabular data. So this is what word count looks like with data frames and SQL. This library gives you two DSLs, essentially. This data frame abstraction and the fact that you can write straight up SQL code to query your tables. So my data frame example is fairly similar to my RDD example. We say select instead of map, and we pass functions to operate on our columns. Right, so here I have this explode function that is going to take every column created by split and turn it into a row. And then I do my group by, my count, like our previous examples. You'll notice that our columns are referred to with strings. Some people don't like that. There's a data set if you want to avoid stringly typing your columns. And then here we have, at the bottom, we have the SQL version of word count. If it looks a little painful, that's because it was very painful to write. I don't really recommend it. But essentially Spark provides you an SQL DSL, and you can use this tremendously powerful framework and just write DSL to manipulate your data with. And this opens up the world of data frames and then Spark to your data scientists, your BIs, right? So that's pretty cool. But that's not all data frames do. There's a couple of underlying things in data frames that make them a lot more powerful than the RDDs we're used to. So the first one is Catalyst. So to motivate Catalyst a little bit, think about we're writing a query, we have a table of students and we have a table of classes, and we want to know which students are taking CS 100. So we take these two tables, we join them, we filter by class, and then at the end we really only want to know the student ID, the student name, the class ID, and the class name. But we're smarter than that, right? We've taken these two giant tables, done this huge join in memory, and then pruned all this data out. That's not the most optimal way of doing this. While this is like the most simple example, we can write more complicated queries that we don't really understand all the optimization behind. So Catalyst, like all your SQL servers, is a query planner and optimizer that will go through your queries and optimize them for you. And so I will dig into it a little bit because I think it's interesting. What you get when you write a data frame query and an SQL query is this abstract syntax tree, and that gets passed to three optimizers. The first one is the analysis one, and all this does is kind of parse your column names, your table names, and make sure that they exist in the catalog, and make sure that you're doing correct type comparisons or what have you. The next, once that's done, it creates a logical plan, and that gets passed to the next planner, which is the logical planner. So this is where a lot of fun happens. There's about 100 rules that get applied to your logical plans. So stuff like, I said, the filter, right? So the filter will get pushed down as far as possible. If you're using a JDBC driver, it actually gets all pushed down all the way to the database. It will do projection pruning, which is getting rid of the columns it doesn't need as soon as possible. It does Boolean simplification, which is like your truth tables where it gets rid of the ands and ors that you don't need. So those are like 3 rules. There's about 100 that get applied, and it'll give you, at the end, an optimized logical plan. So once that happens, your plan then gets passed to the physical planner. And the physical planner decides where your data goes. So you remember that we're dealing with RDDs, a big cluster of machines, right? So the physical planner contains maybe a dozen rules that have kind of little fuzzy logic. There's functions like is big enough. And it decides like how to do your joins, how to do your sums, how to do your averages. It'll decide a table is big enough that I should hash my keys and put them here and here, or a table is small enough so I should just ship the whole table to every node. So once the physical planner has generated a bunch of physical plans, it chooses the best one based on a cost model, and then we'll actually generate RDD code to execute your query. So that's Catalyst. It's the query optimizer in data frames. And then there's a second really cool thing inside data frames called Project Tungsten. Project Tungsten isn't like a framework or a thing like Catalyst is. It's a long series of very low level optimizations. So to think about Project Tungsten, you have to imagine, close your eyes and imagine 2008 when Spark came out. So in 2008, Obama was just elected. It was the end of racism. And our EC2 servers were 3 gigahertz processors, 10 gigabit network speeds, disk-based hard drives, right? And now we're 8 years later, Hillary's gonna be president. It'll be the end of sexism. Our hard drives are SSDs or striped disk drives. Network speeds are like 10 times better, but our processors are still 3 gigahertz. So Spark is actually limited by processor speeds now. So Tungsten is an ongoing project to fix that. So I'll give you some examples of what optimizations happen underneath the hood in Tungsten. So there's a series of binary processing optimizations. If you think about a string, a 4-byte string, right, like ALEX, we know it's 4 bytes, but on the JVM, there's a lot of overhead that turns it into 48 bytes. So there's like 44 bytes of overhead. And so most applications, that's okay. We can deal with a bunch of overhead for big strings. But if we're dealing with millions and millions of strings, this 44-byte overhead becomes kind of unmanageable. So a lot of the optimization involves having binary representation of basic values outside the JVM. So if you're curious, it uses sun.misc.unsafe to to access it. So a lot of values are stored in binary format outside the JVM. And because we can do this, we can also manage the memory explicitly. So Spark has an explicit memory manager. And the way this works is, you'll remember Catalyst has a very specific execution plan for our data. We know exactly when we're going to need our students table, and we know exactly when we're going to not need our students table. So using our plan and the fact that we're managing binary data explicitly, Spark can say, okay, I no longer need this, wipe it right away. The third large group of optimizations is cache-aware computation. And so with what this means is, when we do any operations, disk I/O is kind of our problem, right? We're waiting to read and write to disk. But in some operations, what's actually slowing Spark down is reading and writing to RAM, right? So waiting to read from memory is actually the bottleneck in some cases. So the way that's gone around is to use the onboard chip cache to do some operations. So an example is sorting key value pairs. So if you imagine a traditional key value pair, your keys and your values are stored in memory, and you have an array of pointers to your keys. And to sort them, you have to dereference 2 pointers, retrieve the values, compare the 2 values, and this is just too much, right? What cache-aware computation does in this instance is, we're actually going to store the keys in cache and sort the keys in cache. And we're never dereferencing the pointers to do this sort. I'll stop talking about Tungsten here. Like Kevin Weber said, if I keep talking, I'm going to get myself in trouble. So if you're really curious, there's like 100 issues in Tungsten that are fixed. The JIRA is Spark-7075. So data frames open up the world big data to your BIs, your data scientists, but it also gives you tremendous performance improvements over the base RDD abstraction. And what's really cool is that it makes all the supported languages fairly equal in performance. And this is an old slide, an old graph that they've shared around. What's the numbers being thrown nowadays is that data frames are within maybe 20% of native C++ code in performance. Okay, so finally, in the last part, we have enough context now to talk about the new structured streaming library. So Spark 2.0 released like 10 days ago, has the alpha release of structured streaming. And the alpha release basically just contains like a steel thread, an A to B minimum implementation of the idea of structured streaming. So if you check out the API, there's like 5 method calls. That's it. So structured streaming, from the back of the box, it says structured streaming provides fast, scalable, fault-tolerant, end-to-end, exactly one stream processing without the user having to reason about streaming. So these are like some pretty big claims, and we'll look at a couple of them in detail. The classic model of streaming, when streaming first came out, is we're getting some data, we're going to do some ETL, and we're going to dump the results of ETL into a sink somewhere, and somebody will eventually use it and do something with it. But in practice, a lot more is being done with streams nowadays, right? We get tons of data, we still do our ETLs, we report to some dashboards, we do some live querying to see the state, our window, and we maybe have a machine learning model that we're training on new data as it comes in without having to shut it down and retrain it on a whole batch. And so while this idea of a continuous application is totally possible with the stuff we have now, it involves a lot of scaffolding, right? You're putting a lot of different parts together to get this done. And so what structured streaming wants to do is to make all of this into one unified API where you don't really have to think about the fact that it's a stream. And the way we're doing this is to think about our streams no longer as a stream, but just as an infinitely growing table. So every time a new data comes in, it's just being appended to this abstract table that we're thinking about, and the table is just growing as data is coming in. So a word count in structured stream would kind of look like this, right? We have input coming in from a console at some interval. That input is being appended to a table. We're doing our fun word count. This gives us a result table, and we're outputting the result table to console, files, smoke signals. So if you look at this and you go, hey, this result table is just going to grow infinitely, what's going on? The answer is yes. It's growing infinitely in 2.0. In 2.1, they're implementing a feature called watermarking, which will kind of eliminate, give you the ability to prune data as it goes along. So what does the API look like for this? So this is the structured stream word count. If any of you are actually drinking, this is like number 7. So what's happening here? I mentioned earlier that SQL context was your entry point into Spark. So in 2.0, there's a new entry point called Spark Session. And Spark Session will now be where you get your SQL context and your Spark context from. So you can see on the line that says lines equals spark.readstream, the read stream is a data frame reader. So it's reading this directory as if it was a stream of data frames. And then I have the next 2 lines here are my word count, right? I'm splitting up my sentences, and I'm grouping by value. Value is the default name for columns. And then I'm counting my words. What's really cool here is that it's a stream. I don't have to think about the fact that it's a stream. and my word count would work exactly the same whether I was doing a batch job or a stream job. I would not have to change these two lines at all. If I had wanted to write straight up SQL to do this word count, that SQL would work whether it's a batch job or a stream job. And the way to change this from a stream to a batch is in the spark.read stream to just get rid of the word stream. And that would become a batch job without having to change anything else. I also don't have to worry about fault tolerance, right? Because we're saying end-to-end exactly once guarantees. So what does that mean? That's a big claim. So we'll look at this Kabbalah and try to explain how we can say end-to-end exactly once guarantees. So you remember Catalyst, which is our query planner. We're also using Catalyst now to plan our streaming input. So every time we're computing new input, Catalyst is going to create a plan for us. That plan will get stored in a write-ahead log. That write-ahead log is backed up by HDFS files. So if at any point during execution I fail, I can always go back to my plan, reload the plan, and know exactly what I'm going to do. In my word count, I'm maintaining some sort of state, right? I'm maintaining the table of words and how often they're used. If I fail, this state is also stored on HDFS using a state store API. So it's a bunch of Delta files that are stored in HDFS. So if I fail and I need to retrieve the last instance of word count, that's where it is. Some of you might say, but Long, what if HDFS fails? Then you're right. Then we have exactly 0 semantics. So that's our execution, the internal state of Spark. So we have two big question marks left, right? Source and sink. The API for source is going to be a little different now from other streaming APIs for source in that it requires replayability. So if my state fails, I have to be able to go back to source and give an offset and say, scroll back 10, replay the last 10. And sinks are going to be a little bit different too. Sinks, so I didn't think somebody would use this word this weekend, but Mike Nash did. So sinks have to be idempotent. And idempotence in streaming means that no matter the amount of times you get the same message, you have to be able to provide the same result. All right, so if you get the message once, your state will look like this. If you get this message twice, your state will still look like this. So with the combination of sync idempotence, source replayability, query planning that's backed up by files, and state that's backed up by files, there's an end-to-end exactly once guarantee in structured streaming. So it sounds like I went fairly fast. So conclusions, structured streaming does data frames, and you can write SQL for your streaming applications now. You get Catalyst for free, you get Tungsten for free. You have this unified API that will do batch, will do streaming. In the future, will let you do machine learning and graph computation in incremental ways. It opens up the world of Spark to your BIs, your DBAs, your data scientists. Some people have mixed feelings about that. You have exactly once guarantees. You no longer have to have this mental load of thinking about the fact that you're doing a stream versus a batch job. And I didn't talk about this, but there's event time primitives that handle late messages in a much better manner. So as I mentioned, 2.0 is the kind of the alpha, the steel thread, minimum viable product of structured streams. In the future, we're going to have Kafka integration, they'll release a public API for sources and sinks, watermarking to prune our results table, and machine learning integration. And if you want a copy of these slides, it's on my GitHub. If you want to hear me tweet about food and A Song of Ice and Fire, please follow me on Twitter. And it's long Tran with 5 O's. And that's it. And there's a long list of sources at the end.